Let's imagine that we have a container of 3 kilograms of liquid water, and it starts out at 20 degrees centigrade. And then we've got a block of copper, let's say a 1 kilogram block of copper, and I'll just let us know that the specific heat of copper is 387 joules per kilogram degrees Celsius. And the copper starts out at 100 degrees Celsius. This is actually a very, very common type of experiment that is often done in physics labs, and it's one that we do here, where the sample is put into a steam generator that's got boiling water, and we allow the sample to stay in the boiling water, which we know is 100 degrees centigrade, until it comes to equilibrium. In other words, we let it sit there for quite a while, so that we can assume that the initial temperature of the sample is 100 degrees. We then take it out of the boiling water, dry it off very quickly, put it into the cooler water, and what's going to happen? Well, the sample, which is at 100 degrees to begin with, we put it into 20 degree water, the sample is going to cool down. The water is going to heat up. Energy is going to go from the sample, it's going to leave the sample into the water so that the sample cools down, the water heats up. Let's see if we can't figure out what is then the final temperature. What is the final temperature that the water and the sample, the copper, will come to? So we will assume that we wait long enough until all the energy that is going to leave the copper leaves it and goes into the water. So the water heats up as much as it's going to, the copper cools down as much as it's going to. But we're going to make an assumption here. We're going to assume that there is no heat coming into the system nor leaving the system into the environment. We're going to assume that it's an isolated system. So imagine that we have maybe have this in some kind of insulating cup or something like that, so that no heat will go in or out, or at least very little that we can ignore. Also, we're making another approximation here, another assumption, and that is that the cup itself does not contribute to the heat exchange. That's not necessarily a good approximation, but just for our first calculation, we will assume that. For the lab that we actually do here in our lab, we actually take the heat capacity of the inner cup into account as well. But just for now, we won't. What we will do then is we will assume that the heat change of the water plus the heat change of the copper is 0. So this is basically our assumption of the conservation of energy. In other words, whatever energy is gained by the water is lost by the copper. So one of these will necessarily be positive, the other must then be negative. Well, we expect the energy of the water to increase, so this will be positive. We expect the energy of the copper to decrease, so this will be negative. Both of these represent temperature changes of the material, so for a temperature change, we know that Q equals mc delta T, so we'll have Q of the water is mc delta T of the water, so this will be mass of the water, specific heat of the water, delta T of the water, plus Q for the copper, that's going to be mc delta T for the copper, so this will be mass of the copper, specific heat of the copper, delta T of the copper. And all of this then must add to 0. So let's put our numbers in. What do we have? We've got mass of the water, that's 3 kilograms. The specific heat of the water, that's what I said, 4,186 joules per kilogram degrees Celsius. Delta T of the water. So what's the temperature change of the water? Delta T of anything, as we've said, is always the final value minus the initial value. So what's the final value of the water? That's what we're looking for. That's what we will call TF. So this will be TF minus the initial value of the water. What's the initial temperature of the water? Well, that was 20 degrees centigrade. So we'll put in minus 20 degrees centigrade there. Plus mass of the copper. Mass of the copper is 1 kilogram. Times specific heat of the copper. Okay, I've said that is 387 joules per kilogram degree centigrade times temperature change of the copper. What's temperature change of the copper? That'll be the final temperature of the copper, which is the same as the final temperature of the water, we're assuming, TF, minus the initial temperature of the copper. Now, what's the initial temperature of the copper? The copper is starting out at 100 degrees centigrade. So, minus 1, whoops. And then all of that must equal 0. Well, let's notice, we expect, what kind of value do we expect for TF? Well, if the water is heating up, we expect TF to be larger than 20 degrees. And if the copper is cooling down, we expect TF to be less than 100 degrees. So if TF is greater than 20 degrees, this will be a positive number. But if TF is less than 100 degrees, that's going to be a negative number, which is exactly what we expected. So we'll have a positive number plus a negative number equals 0. Just as an aside, what is often done as an experiment is the final temperature is actually measured, and then if you know TF, you can use those values to figure out what the specific heat of the material is. So if you don't know what the specific heat of the particular sample is, you could do this experiment and actually measure TF and then use that to calculate the specific heat of the material. But we're not doing that. We're assuming the value and using it to calculate TF. So let's multiply these out, and what do we get? So we take 3 times 4186 times TF, and we get 1.26 times 10 to the 4th joules. Now notice the kilograms cancel here. Joules TF times per degree Celsius, so joules TF per degree Celsius, minus, and then this times negative 20, and that gives us minus 2.51 times 10 to the 5th joules, and then plus, multiply this times TF, and we get 3.87 times 10 to the 4th joules, and then times negative 100, and we get minus, whoops, sorry, I switched those around. Let me write this. This is 387 joules TF per degree Celsius, and then minus the 3.87 times 10 to the 4th joules, and all of that must equal 0. There we go. Let's combine the joule TF per degree Celsius with the joule TF per degree Celsius term. We've got these negative terms. Let's bring those over to the other side. And what do we get? I'm going to erase this part up here. What do we get? We end up with 1.30 times 10 to the 4th joules TF per degree Celsius. And that equals these terms brought over to the other side, which are 2.90 times 10 to the 5th joules. Divide by the 1.30 times 10 to the 4th, and we find that TF is equal to 22.3 degrees centigrade. Celsius, there we go. All right, very, very good. Let's just take a look at this just for a second. We notice 22.3, that's not much bigger than 20. And it's much less than 100. Why is it that our final temperature is so close to the initial temperature of the water? Well, there's a couple reasons. First of all, we notice that we've got much more water than we do copper. We've got 3 kilograms of water, while only 1 kilogram of copper. So we expect the temperature change of the water to be less. But also, we notice the specific heat of the water, which is 4,186, while the specific heat of the copper is 387, the specific heat of copper is much, much less than the specific heat of water. It's less than 1/10 of that of water. Water actually has a very, very, relatively, very, very high specific heat. So those two effects combine to make the final temperature much, much closer to the final temperature of the final temperature is much, much closer to the initial temperature of the water than it is to the initial temperature of the copper. Okay. Very, very interesting. Let's take a look at something else now. We said that these temperature changes can only be so large, or else we'll have some changes in the material. Well, that is something we'll take a look at now. What happens if we cool water down so much that it goes below 0 degrees, or we heat water up so much that it goes above 100 degrees? What happens in that case?